All right, so let's check something a little bit. Greetings wherever you are. My name is Biba Bright, and uh, today I'm going to look at another way of checking antibiotic resistant genes using a tool called Abricate. So I'm going to share my screen pretty soon, and then we look at how to use Abricate to also check for antibiotic resistant genes and virulent genes that are found in the genome of either a bacteria or any other pathogen you can think about. But before I continue, please do me a favor and subscribe to this channel, share it, comment on it, whatever you think, and I will take what I will take that you are assisting me by doing so. All right, now let's go straight to the point and then see how. So I'm going to roll out my. I hope my screen is visible now. So let me clear my screen in the first place, and then so this is if before you'll be able to use Abricate, you must have what is it? You must have a Linux platform, and then this is my Linux platform that I am using. Uh, I decided to change the color just for the purpose of visibility. So first of all, I'm going to check whether if my Abricate is installed. So I'll just type Abricate and then I'll enter. And then as you can see, it is installed. And one of the ways to use these tools in Linux is to make sure that you come to look at this portion called usage. So it tells you. So if you want to check uh, for anything at all, look at how it is being used. You have the aggregate here, you have options, you have context. It can either be a FASTA file, GBK, that's GenBank, or Ensemble. And then it can even be a zip file, and then you have your output. Then you can also have your summary in the case you have more than one aggregate, or sorry, more than one quantic or more than one FASTA file, and you want to check for the presence of the virulent or antibiotic resistant genes. So first of all, what I'm going to do is I want us to know that the antibiotic resistant genes are coming from databases that have done this over and over, and they have resourced their database with all these genes which are there. So what Abricate is doing is to simply pick your genome and align it to the database, and when the sequences match, then it retains the gene for you. And because of that, we have several databases which we use for for checking our AMR genes. So to check for the databases which are available, usually when you install Abricate, then so we can just use this part. We use this code called Abricate, then you leave a space and then dot list, and then we enter. So to be able to check the number of databases, because when I install it, uh, it's different from maybe when you install and the version that you are using. And then when you check the databases, then you will know that these are the databases that are working with the Abricate that I have installed. And so as you can see, I have my database here. I have Argonaut, I have CARD, I have Echo, I have NCBI, I have Plasmid Finder, I have resistant, what is it, a REST Finder, and then virulent database. So these are databases, and we can check when they were updated. 2016, 20, some of them were 2016, 2016, they were updated 2016 as far back. And so that is it. Now we know how Abricate works. So if I go back to the usage, then we come here and see, let's pick this particular code, and then we see how we can put it there. So what I'm simply going to do, if I come, I need to check for my, or the let's say the FASTA file that I have, or the GenBank file that I have, or whether it is a Contic or whatsoever. And then we have this FASTA file which is already seated. Let me try and see whether if I can fly something. I'm trying to see whether if I can get that FASTA file. I think is fly something something, and then I'm trying to see whether if I can get it. So yeah, I think it's found in my downloads. And then what is it? Let me check and see if I can find it. It's actually a file that is seated somewhere in my downloads. And if I'm able to get the file, then we will try and check within that file if there are some. It's actually a FASTA file. We will check for the antibiotic resistant genes which are present in them. Yes, and then so I'm checking for that pretty soon. I want to find out whether if it is there. Okay, so I'm just going to use this. I think, okay, so let me check. And so I'm going to use my Abricate first of all. But sorry, I was checking for fly. I was checking, so I'm going to check to see whether if the the FASTA file is actually present in my current working directory, which is download. To check your current working directory is pwd, and you can see that my current working directory is downloads. So I'm going to check in my downloads if I have a file called fly underscore. So we have fly. So now let me use head and just print some few lines head like this, and then I'm just going to print only 4 lines, and then I'm looking at fly underscore something, and then it is there. So as we can see, the FASTA file is seated around here. So it's good. We can now go ahead and then check for the antibiotic resistant genes using all the databases that we have already established. And then we compare the number of antibiotic resistant genes found in each of the databases. Since they have been updated, almost all of them have been dated in 2016. So first of all, to be able to do that, you first of all have to start with Abricate, and then mostly you follow it with the database. On the database is as you can see, I don't know if I have to do the Abricate again. I'll run it again, and then we can see. So we start with Abricate, followed by the database, and then you can follow by your quantic, and then in that order. I have already run these lines, and so I'm just going to show you how it works. And so now this is the code. I have my database, which is seated here, but and then it's followed by, once you indicate a database, you have to indicate this flag DB means database. Which database am I using? I'm using REST Finder, and then followed by the quantic or the FASTA file that you want to find your antibiotic resistant genes from. And then you put this greater than sign to show that this is your output. What is it? That's your output file. And then you want the output file to be in a tab format. I've tried with CSV, and CSV doesn't work. So you start with your Abricate. You go with your the any of the databases that you want. So the first database I want is resistant gene resistant gene finder, and that's the database as you can see it around here. Yeah, and so my output is going to be I think as we change this output, so that's going to be my first output is going to be fly resistant resistant genes finder dot tab. So it's going to be a tab file, and then I'll simply just run it and then see what will happen. So it's going to pick up, it will generate the data or the genes for me, and that will be it has found 11 genes, as you can see around here in the fly. So the next thing is, let's see if we can change the database. And to change the database, I'm going to come here. We have already seen the databases, aren't we? And so the next database we're going to use will be CARD, and that's the comprehensive antibiotic resistant database. And because of that, I have to also change the output file. It's also going to be a tab file, but this time around, I'm going to change it from this to, and then I'll call it card. And so when I do that, I know that this particular gene that I am going to hit is coming from my output file. It will be fly card dot tap. So that way, it will not confuse me when if I have my output files. So you see that it's also running. And so in that particular in card, we found 19 genes. As we can see, the 19 genes are here. And of course, maybe we may want to try another the database, and then perhaps this time around, let's use NCBI. And so the NCBI, NCBI, we use the NCBI database, and then we try to see whether if we can find some genes too over there. And so if you check in all of them, NCBI has about 4,322 sequences, which have already been identified as antibiotic resistant gene sequences. So this particular sequence we have here in the fly assembly.fasta is going to be allowed to those sequences. But when you check the first, the card has about 2,220 sequences, and then NCBI has about 4,000. So you can see, but NCBI rather retained about 17 different AMR genes, and as we can see here. Now let's continue and check for more of the databases. And then I think one of the databases that I know is Argonaut, but I'm unable to spell Argonaut. So what I'm going to do is I'm going to do this Abricate, and I'll just do lists. And then if I get a database, I'll just copy and paste it. So that way. So here is Argonaut. So I'm just going to copy this in Linux, Control C, Control Shift and C, it is copied. And so when I come, I'm just going to go back to this, and then I'll get to the database part, and then I'll change that, and then press my right button, and then Argonaut is set. But I think I made a mistake after running the fly card. Okay, and then which one did I run again? Okay, I have not run anything. So I ran NCBI, but I did not change the output to NCBI. Yeah, it is here. So I'm going to run this, but I'll run the NCBI again. And so this one is Argonaut. So I'll put that what is it? Argonaut. So maybe this one. So let's try this one first and see. After that, I'm going to run the NCBI again, and then make sure that one found about 15 different AMR genes. And so I'm going to change this and then come to NCBI. So the NCBI, I have to run this again, and I'll put here NCBI and then run that again. And then that is going to find how many? Let's see. It's still processing. Some of them it takes a little bit, depending on the power of the. That one also found about 17 genes. Is it already? And so, what is the next thing? Let's check for echo. There's also a database called echo, and then I'm going to check that. So I'm changing NCBI to echo, then and then so the database portion, I'm changing NCBI to echo. Okay, so changing NCBI to echo, or let me just paste it. I think that will be much more better. And then I'll run that and see in echo how many AMR genes we're likely to find. And so it's taking a little while. And in echo, we have just about 596 sequences. So, and because of that, it found 0. There's no AMR gene that it has found. You can see 0. There's nothing in it. So let me see which one. We have used ResFinder. We have used NCBI, which is echo. We have used CARD. We have used Argonaut. This is virulent genes, so we may not be interested in that. But let's see whether we can find some plasmids from the database. So if we can find plasmid from the FASTA file, the fly assembly.fasta. So what I'm going to do, I'm just going to copy this and come here, and then I'm going to change this to plasmids. So we are checking plasmids plus this, and then I'll just go all the way to the database, and I'm saying that in this case I am looking at plasmids. So it's plasmid finder, and see whether we'll find some plasmids. So it's also working now. So we have found about 5 different plasmids, and then they are here. So in all, so we've been able to run all of them using the Abricate, and then we found our gene. So now let's go to my desktop, and then we check for, because when we go to my desktop and I go to downloads, all that, the output files that I have specified, all of them will be seated there in a tab delimited format. So I'll open them with my text editor, that is a notepad, and then I'll be able to visualize them. What is it? And then make sense. So let's go to so if I come here, I go to my downloads. If I come, so my downloads, I'm trying to look for where they might be hiding the output. So you can see all of them are here. This is for Argonaut. This is for CARD. This is for echo. We found nothing, so I'm not going to waste my time. This is plasmids, and then this is NCBI, and this is resistant gene finder. So let's open each of them. Let's start with the Argonaut, and we see how the whole thing works. So this is the Argonaut, and then you can see the number of genes it has found. So to make it easier, I'm going to do it this way. I'm going to come here, open my Excel, and then I'm going to take this, the whole of this column out, and then repurpose it. Maybe I just want to shift it so that it makes sense. It's just too wide. All right, so what I'm going to do, I simply will open this. I'll come here, Control A, and then copy everything. So if I come here, I'm just going to come to this place, and then I'll paste it. Because it's a tab delimited, Excel understands it. So if I come here, I'll open it up. And I'm doing this because I'm going to explain this once, and then the rest I will not waste your time on that. So we come, so we can see the genes that Argonaut has hit, and then in that order, the coverage, and then the database, obviously it is always here, as you can see. So we come to the accession numbers, we have been taught. These are the accession numbers. So I'm just going to highlight the first row, and then I'll just click this and then make it red so that we can see it quite visibly. So this is the output of Argonaut. The first one, the file, are the genomes that we have. So fly assembly, as we have it over here. So we also have the start, the end, and then the gene. This is the gene name. This is the AMR gene that we are looking for. So this particular column. So maybe I should highlight that column. I think it's just too much. So I should just highlight maybe something like this. So for the purpose of clarity. So these are the genes that we are looking for. And as we can see, now let's look at something here. In Abricate, the first one is always the file name. Now, here is the sequence description. Is it a contig? Is it a complete genome? Is it a whole genome? It will be indicated. And then these are what? It is a contig. And here, that's the first contig, is the contig 1. So we had contig 1 and then contig 2. So in the first contig 1, if we want to group all of them, like we saw, I could have actually done this, and then maybe come and look at the genes which are what are corresponding to it, and then we can begin to have. This is just small. So if you want to check for how I visualize genes, I have already done that particular video is here. You can look at how genes are. So now here it will describe the sequence, which is a contig. And then we can see the number of the contig 1 and then contig 2 here. Then we have the start. The start tells us which part of the genome did this particular gene is found. It is found between this set of sequences from the 222,734 nucleotides, and then it ended around 273,151. So this is the range of sequence where this particular gene is lying. And that's what I want us to pay attention to. So when you see the start and the end, it tells you the range within which the gene sequence was found in the database. And that's why this particular gene was hit. To know whether, now when we come here, this is the coverage. And then what the coverage simply tells us the total number of sequences that were covered, like I have just explained, from our sequence. And then when we go ahead, we can see the genome map here. It actually tells us about three important things. When you see this equal sign continuously, and then you see this particular slash here, it means there was a gap. There was a gap in the alignment. And see, when you see dot like this, it means it was not aligned. The alignment was poor. You can also see another one here, which was also poor. So the alignment was not there. We can go to Abricate data, website, and then we can see all this. So we can see the gaps. And usually when there is a gap, it will just write the date for you. And now the coverage is also here. The coverage tells you the total number of sequences that were covered from our genome. In the reference? It tells us the gene coverage. And then this one tells us the nucleotide coverage in the genome. I'm going to go to the database itself, and then we see these are the accession numbers. This particular accession numbers, when we pick them and then we go to NCBI, we can actually find this particular gene, which is also there. And then the product. The product is usually the specific antibiotic that is resistant to this particular gene. And Abricate has done something quite well. The gene is actually inside, but whatever that is outside here is much more of the same thing that you see here. That is practically the antibiotic that it is resistant to. So as you can see, the gene is black, but the antibiotic is maker A. And so you can see the gene here is MLS, but the antibiotic it is resistant to is erythromycin A. And then we can see AGLY, and then the antibiotic is here. We can see this place is, what is it, tetracycline, that's the, which is having the subtype of 38. And then the same tetracycline here with the subtype of A. So in that order, when you see it's the same thing that is here, maybe if I could expand this a little bit, then you will see it. So this is basically how to be able to read this particular table. And this is how we use Abricate to be able to hit our antibiotic resistant genes. So I'm going to come here and then I would, this is the fly. So I'm going to leave, but it's the, so I'm going to open a new sheet and then I will go back to this place and then I'll open the card and then let us also look at the card and see what is there. So this is also the card when we use the comprehensive antibiotic resistant database, which is called CARD. So I'm going to highlight that. I'll copy it and I'll take it to my Excel. My Excel here. Oh no, I'm opening a different Excel. It's here. And then I'll simply come and paste it, which is here. So when I paste it, you can also see that it's the same sequence, but in this case, we are having more genes than the other one, if I'm not mistaken. So we can see the total number of genes that we are having from about 17 different genes that we have here. And this is the NCBI database. That's the NCBI. The database will be indicated there, which is NCBI. I'm not going to now explain this. There is still the same thing, except to point out to us here the product. So this place, let me highlight and extend it so that we can see the product quite clearly. So this is the gene, like the first D is the gene. But if you notice, you have fosfomycin resistant. So this is the antibiotic that it is resistant to. You come here, the antibiotic. Most times, if it's not able to tell the antibiotic, it will tell you the type of resistance that is there. And it can be E-flat pump, it can be beta-lactamase, it can be other forms of resistance that it is there. And then here, as you can see, is penicillin. And then as I was talking, that's the beta-lactamase sensor or signal transducer, and then in that order. So here, the product describes the antibiotic that the gene is resistant to, as well as the way, the manner in which the resistance takes place. You see, it can, if it is beta-lactamase, it means that there is an enzyme that actually degrades it or makes the antibiotic ineffective. If it is E-flat pump, it means the antibiotic, the gene is able to pump out or to assist in pumping out the antibiotic when the person takes it, and then in that order. So this particular product gives a lot of information about this. I've already explained this. So that is it. So let me open another Excel sheet and I'll go here. This time around, we're going to look at the echo, but it's like in the echo, we found nothing. There was no gene. So let me quickly go and look at the resistant gene finder. And so I'll just highlight it, I'll copy it, and then I'll simply come open to this place, and then I'm just going to paste it there. And as you can see, the genes too are also here. In all of them, you can see the first Z is there. So what I would have done is to copy these genes and then put them line side by side to be able to compare them. And then I could just copy this and put it one side, copy the one from NCBI and put it, copy from CARD and put it, copy from Argonaut and put it. Then I'll compare which one is existing in one and which one is not existing. And then I'm able to make a case. And then apart from that, we should not forget about these gaps and then the unaligned. So it means this part of the gene was not aligned properly. The other part was aligned. So when you see the double equal sign going, it means that part was aligned. And then if you want to know what was the coverage, then you can come here and then look at the start and then the end. And then the coverage too, you can come and read it around here. So when you see that the unaligned, you can see that the coverage is always below 50%. And of course, if it is below 50%, then we have a problem accepting the gene. And then, but here the identity is around 99.9%. So that gives us a little bit of confidence. But when two of them, both coverage and identity is low, then the gene become questionable. And as we see, we can see the product, which is also here, telling us the kind of, so this is tetracycline, this is erythromycin, and then in that order. I've forgotten what this AAC is all about. So basically, some of the genes too, it also carries the same name like the antibiotic. So it can be the gene, and then obviously when you look at it, you can deduce the antibiotic it is resistant to, like this FOSD_1. If you check, there's an antibiotic with this kind of a name, what arrangement, and that's how it works. So basically, this is how to be able to check for antibiotic resistant genes in all the databases that are found in Abricate. Most of these databases, they can stand alone. They can stand alone by themselves, and then you can use their web servers to be able to deduce this. But this is, if you are good at Linux, this is the simplest way to be able to do that. Now let's look at the last one, and then I will leave you, and that will be the plasmids. We also check for some plasmids, and let's see what are the plasmids which have been found there. And so I'm just going to copy that and then take it to my Excel. Okay, so I'll come and paste it here. So it makes, when you bring it to Excel, it makes the reading a little bit easier. So it's a Quantic. So Quantic 1, we can check here, even though it indicated the plasmid a gene, but actually these are the plasmids. So we can see the plasmid here, we can see the plasmid there. Maybe let me highlight it a bit so that we can see. So we were able to find about 4 plasmids, which I have highlighted here, and as you can see them around here. And then we can check, so we use the plasmid database to be able to do that. The accession numbers are here, which is very important. And then we can look at the product. This plasmid, what are they contributing to? So obviously, we do not have a specific product to it, but the same plasmids have been repeated. But we know what plasmids contribute to. These are actually the smaller part of any gram-negative bacteria, and we know that they have the capacity of manufacturing their own mRNA, which actually instructs the ribosome to produce their own genes, which is resistant to antibiotics. So the more you have plasmids, then there is a potential of the production of antibiotic-resistant genes. So here, when we check in this particular Quantic or this particular isolate called the fly assembly, it's actually Staphylococcus aureus. Then we notice that these were the number of plasmid that we found in Quantic 1, and then this particular Quantic, Quantic 2, Quantic 2, Quantic 2, and then in that order. So basically, this is how we are able to check for antibiotic-resistant gene, plasmid, find what plasmids, and then in a FASTA file or in FASTA, multiple FASTA files. So let me get back to this place and then explain something. Now we have indicated this one, we are dealing with only one sample, and that is the fly underscore assembly. What about if we were dealing with so many samples? Basically, it would have been the same. But here, let me clear my screen some more. Here, we would have been looking at aggregates, and then we would have our database, and then we can indicate the database, let's say NCABI, and then it means that we would have our folder seated with all the FASTA files. So what we would have done, I would have just indicated FASTA like this, and then so that when it goes into the database, it picks only the FASTA files alone, and then it's able to run with it, and then it will give us a summary. I have done that quite a number. It can run as many as possible at a time. Then after I have done this, then all I need to do is to simply bring my greatest time, and then I will say summary.tab. I left a space here, summary.tab, and then that's all. So if I run this line, it will go and then check for all the FASTA files which are there, and then it will generate all the information that I have shown you. I have shown all of us here for all of them. So maybe this would have ended for, let's say, this particular what isolate called fly assembly. Maybe the next one would have been called maybe flying something, or would have been called a different, or maybe a different isolate or a different strain. it will continue from here. Then another one will continue, another one will continue up to the last one. If there are 100, there are 500, it will continue like that up to like the 1,000 that you have. And then the same information would have been here, but the number of rows would have been so much. The last time I ran, I had about 22,000. So you have about 22,000 rows, and then that is when you have to visualize the genes. But for here, there are just few of them, and then it's easy for us to be able to make sense. But if the genes were like, I'm talking about like 22,000 genes, AMR genes, then you have to find a way to be able to make sense from it. And I've already done a video as to how to be able to make that kind of sense. If you have not watched that video, please try and do that. I think, let me show you. I don't know if I have, because the genes were just too many, this is how I decided to visualize it so that so these are the virulent genes, these are the AMR genes, and the genes were like 22. So, but you will notice that some of the AMR genes will be repetitive. So I find a way to produce a heat map for us to be able to see where they are much more conspicuous and then where they are sparingly present. And that's how it works. So, ladies and gentlemen, this is how we can use Abricate to be able to generate our AMR genes just like the way we want. We can check that for all the databases. Thank you, and I will see you some other time. Please do me a favor and subscribe to this channel, and by doing that, you are assisting me. My name is Biba Bright. I'm a bioinformatician, and I do data science as well. Thank you. See you some other time.